Okay, hello and welcome to this new video. In this one, I'm going to discuss the electronic power supply board, or rather design, and I'll present what I've come up with and how it's going to integrate into the project. So basically, here I have opened my GitHub repo for the project, CubeSat project, and you can see we have, of course, different subsystems, and today our focus is going to be on the electrical power supply, rather the EPS in short form. So basically, the EPS is responsible for the most important job, which is supplying the power to the components of the CubeSat. So basically, which includes the energy generation, energy conversion, regulation, storage, and then distribution to the load, or loads in this case, because we have different, or rather several boards or subsystems that we need to supply power to. So based on my research, there are methods, several methods. I've come across several methods to do power generation, and these are the functions listed: storage, conversion, etc. And the recommended approach from one of the universities was that first we define the power consumption characteristics, rather the power budget. How much do we need for the CubeSat? Next, we define the necessary generation and energy storage required. How do we store that energy that is generated from the CubeSat? And next, the number three is we select the methods of generating and storage. I think these two are very close. The next one is, as I've mentioned before, power budget and the profile based on the start to end of mission. So when your mission starts, how much power are you going to use? So that you know now, if I'm going to be in orbit for the next 5 years, how long can those batteries last? The components I choose, how long can they last? What's their lifetime, etc. Things like that. And now the number five is that you design, after doing all these constraints analysis, you design the power conversion, management, and distribution systems, or other schematics. Obviously, the next three are straightforward: you procure, test, and then uh, produce your final board. So you can see I've listed that there's isolation testing, and then there's integration testing. So isolation testing is when we do tests on specific components to maybe probably stress test them and see how they behave in isolation. You can test the batteries to see their rate of discharge if they have been told, been said in a data sheet that they will provide, let's say, 10C discharge rate. You can test that and see what's the theoretical, what's the practical C rating. Then integration test is after you're done with testing all these components, then you join them together and do a full-on test, like stress testing again, and see whether these components communicate with each other as you desire, as your design needs. So there's a lot of information that can be discussed in respect to EPS, but I'll keep it short. So most of these parts have not been filled yet. I'm in the process of writing them, or rather documenting my findings. So next, I'll now discuss the schematics. No, it's not the schematics, the flowchart that I've come up with in regard to this design. So where is it? Schematic. Yeah, there is. So I hope you can see this. Yeah. Just a minute. I export. Let me just export this for ease of sharing. File, export as a PNG selection. Export. Let me export to desktop, save. Okay, they'll open it. Should open. All right. Here we have block diagram. So as you can see, this is a very basic block diagram showing the electronic power supply design that I've come up with. This is from scratch. I've not now I've just tried to fill in some parts based on what I need on the EPS. Now, my mode of generation is the solar panels, as most of the CubeSats do. That's not a new one. So solar panels are used here, and I'll actually explain Windows. I'll explain each block diagram or other component, but I won't go into details yet. Maybe in the next video. This video is supposed to be very short and to the point. So the power generation part, this part here, these are solar panels. So I will design the solar panel scheme later. You can have as many as you can fit into a given space based on the efficiency and the wattage and the voltage and current that you can generate from these other voltage that you can generate from these solar panels. That's a topic for another time. Now, from the solar panel, we have what we call this is a switch. It's an inhibit switch. So an inhibit switch is a switch used on these such systems like CubeSats to prevent or to block off a given part of the circuit so that it does not turn on until that switch is obviously activated. Now, most of the time, rather all the time, I think these inhibit switches are pressed by the deployer, which means that once you insert the CubeSat into the deployer or the P-pod, my last video discusses the deployer and how the CubeSat is integrated into it. So once you insert the CubeSat, this switch is pressed by the CubeSats, by the deployer's edge. So basically it will turn off this channel, it will turn off the channel. That goes for these other two switches down here. So it is basically as an normal switch on off, but they are mechanical switches that are pressed by the deployer. Okay, so after this solar panel, we go now. This here is it's more of a distribution board. There's no function or use. Basically, it's just like a distribution board for connecting different wires. But since this will be a PCB, then these are block diagram construct. Anyway, solar positive, I've drawn lines here to show that it goes to what we call the MPPT charging control IC. So this IC is used to control how the solar panel charges the battery pack down here. So it does things to do with over voltage monitoring, under voltage monitoring, short circuits, etc. such. So it's a charging control IC. Basically, the other thing you can see, it has the maximum power point tracking, which means that it will extract as much voltage as it can from the solar panel. Most of the time, how this is done is that you set this charging control IC to a minimum voltage such that even when the solar panels are receiving the minimum voltage they can register, they can still charge the battery, right? But there are other more advanced MPPT algorithms to do that. Okay, so from the solar panel, inhibit switch, charging control IC, then we have the battery. This is now the energy storage battery. Now, how is this power supplied? So from the battery, we go to the RBF switch. This is the remove before flight switch, which is remove just before the CubeSat is integrated into the deployer. Then we have two more inhibit switches. I've mentioned that. I've discussed what their job is. Next, we go to reverse protection. Now remember, these batteries are like you can remove them from the board. So when you're inserting them into the board, assuming worst case, assuming all of these other items are on, and you insert the battery pack, the reverse direction for some reason, then this reverse protection should kick in and not allow reverse connection to these boards at this other side ICs. From the reverse protection, we have the voltage supervision IC. So the voltage supervision IC is used to, okay, let me explain the problem. Problem is that when you are using a boost converter here, the boost converter is used to boost, obviously, small voltages from the battery so that we can get enough voltage to the load. Now, the battery, these are lithium ion battery pack, so it can go from 4.2 typical 3.7 to a minimum of around 3 or 3.4 thereabout. So you don't want to be stressing the battery to the smallest value by just boosting it, even when it's at 3 point, let's say 5 or 6 volts. So the voltage supervisor IC is like a gate that waits until the battery is at a given voltage before you can boost the voltage, right? So it's more of prevents you from sucking everything from the battery pack. Yeah, but I will explain that later when we are discussing the schematics for implementation. Now, after that, we have the boost converter. I think this is directly, I mean, this can be understood. Boost voltage, output voltage is higher than the input voltage, obviously. Then we have the load current monitor. This is my own implementation I've put here to show how much current is being drawn from this EPS board. Then we have that line goes to the PC104 standard. Now, this board will require some data points. Rather, we'll be collecting data from this EPS board. The data packet, as I've mentioned, is I've written here to be determined because some of this data might or might not be available, but I'll try and make sure that I can get all these data points. So solar voltage, which is basically this voltage from the solar panels here, I've called it V bus, the one that is used to charge the batteries. Then obviously the most important thing is the battery voltage. What's the voltage available? System voltage is the voltage that is going to the loads. Transistor ratio, this is a ratio that is given by the charging control IC that I will use. Maybe in the next video I'll explain that. And then we have the charging current, charge cutoff delay. Basically this means that after the our voltage is detected, how long does it take for this IC to cut off the battery from charging? Don't bother about that. I will go into details next time. Then, of course, the board temperature. You can see I've put two methods of measuring temperatures. You have a temperature sensor and a thermistor. A thermistor, the problem with a thermistor is that it requires calibration most of the time. So I will use it either way just to have these two data points. I can have an average of them or whatever. Then we have a temperature sensor that can communicate most probably by I2C to the control MCU here. Then we have the charge cutoff delay. I mean, I've mentioned what temperature. State of charge. State of charge is basically what percentage of the battery do we have in terms of the voltage. It's like the phone battery. When it tells you you have 30%, your phone is at 50%. It is depth of discharge is a derived quantity from the SOC. So if your SOC is like 50, your depth of discharge will be 100% minus 50. If this SOC is 30, depth of discharge will be 70. Then the last thing is the number of connected boards. So you can see here that I have the loads. So load 1, load 2, load 3. These loads are just the other subsystems like the onboard computer, the communication module. You'll have the altitude and data determination system, for example. So how to implement this is very easy. You have more of like a pull down resistor on each of these boards, and once you insert them, the STM8 can detect this board has been connected. It's like a switch, so you can tell how many boards are being supplied by the EPS. Now, one thing I didn't mention is the MCU. So all of this data packet to prevent an overload on the PC104 from my own, you know, design procedure that I've decided to integrate all of that data into one MCU on the power distribution board, or the EPS, and then send that data from the MCU to the PC104 through the PC104 bus to the onboard computer. So probably I'm going to use I2C for that, because even most of the charging control ICs I've seen use I2C to provide data. So basically, I'm going to integrate all of these data and then send it to the onboard computer through I2C. I think I should mention that there are different schemes of designing such systems, most probably because they are critical systems and you want the least probability of failure. So there's what is known as a distributed design mechanism, and there is what is known as a point of load design mechanism. So point of load means that, for example, point of load supply means that no, point of load regulation means that you don't regulate the voltage on the electronic power supply board, right? You regulate the voltage at the load, at the point of use here. So if I'm generating, let's say, 11 volts from the battery pack, and I need 3.3 volts on the onboard computer, let's say at load 1, I won't regulate it on the EPS, I regulate it here. And you can notice that this board has no regulator, ideally. So all the regulators are connected on the loads themselves. So the other point I'm using, point of load design mechanism, is integrating this MCU. So you can see I've put an MCU specifically on the EPS board to handle the EPS functions. I would have removed this and put this data directly on the bus, but I don't want that. I want every board to be independent in a way, right? And yeah, I think maybe the other parts are these two things here. The solar voltage meter, this IC can give me the solar voltage, but I can also implement my own voltage measuring scheme and read that through the STM. This STM8 is 8-bit, so I've chosen a very small MCU that you know, just for data collection. Let's see, just for data collection. Then current monitoring obviously is also done here, but I know I can get a current monitor from different ICs if I choose the right ones. All right, so that's it with the electronic power supply block diagram. Next time we'll start the implementation part, probably from the battery pack design. So because we need the right design here. You can't use a single cell, obviously. You can't use two cells. You can use two cells, but you can use 2, 3, 2S, 1P, depending on the constraints we come up with, or rather I come up with. So next video probably will be about the battery pack design, and maybe I'll try to finish it in like a single take. But anyway, we'll see. So if there's no other thing to discuss, I am sure there isn't. Maybe I should mention that these inhibit switches are standard. The CubeSat design standard, the CDS, requires that we have them. I've not just put them there for my own design. It requires that you have these redundant switches. Someone might ask, why do you have like three switches in parallel here? I mean, in series here. I'll confirm that they should be in series and parallel. Okay. All right. So if one of them fails, the other one should pick up. I think this should be in parallel for them to be redundant. Anyway, we fix that. But yeah, so there we go. And next time we'll start the design and change this design is not complete, but we will move items different, optimize it as we go. That's it for this one, and have a good one.